Welcome back, statistics scholars. Today, we're going to be talking about regression. And regression is an extension of correlation. That's all it is. It's a mathematical and a conceptual extension of the correlation. So if you feel like you've got your head all wrapped around correlation, which we talked about last time, regression is just a practical application of correlation. And so just like with correlation, it can only be used when you're dealing with two quantitative variables. Well, two or more. The nice thing about regression is, unlike a correlation, which you can only calculate for two variables, you can actually use regression for 3 or 4 or 5 or lots of different kinds of variables. But we're not going to do that. That's what's called multiple regression, and it's the multiple regression or multivariate regression, and that's really a topic for a more advanced class. We are going to deal with simple bivariate regression. Bivariate means two variables, two quantitative variables, because we are just going to deal with the regression case that is an extension of the correlation. But even multiple regression is an extension of the correlation. We are just going to be dealing with simple bivariate regression. Bi means two, like bicycle. Bivariate means two variable regression, where the two variables are both quantitative, where one variable is going to be the x variable. We're going to plot it on an x-axis, and the other quantitative variable is going to be a y variable, and we're going to put it on the y-axis, right? So let's talk about regression. And it is, in fact, mathematically and conceptually just an extension of correlation, except in regression, you have to pick what you think is the cause and what you think is the effect. Now remember how we talked about correlation doesn't imply causation, and that's true in regression as well. Just because you have a correlation or just because you can do a regression with two variables doesn't mean that there is definitely a cause and effect relationship. But the model for regression makes you pick. It makes you pick an x variable that you think is the cause, and it makes you pick a y variable that you think is the effect. A caused B. So using an example from last time, if I thought that eating ice cream was causing people to become homicidal, I would make ice cream intake the x variable, and someone's likelihood of committing homicide, I would make that the y variable, right? So even though there probably isn't, there certainly isn't, a cause and effect relationship between ice cream intake and the homicide rate, in regression, you have to pick one. Which do you think, or which do you want to treat as the cause? Whether it's a cause and effect relationship or not, you're going to treat one of the variables as the cause and call it the x variable, and you're going to treat the other variable as the effect, the y variable. So think of it as input and output. Your x is going to be the input variable, and your y is going to be the output variable. Like input, the amount of ice cream someone eats here, and I'm going to spit out the amount of homicide they're going to do over here. Input x variable ice cream here, spit out y variable homicide rate here. X predicting y. Because that's what regression is for. It's useful for prediction. It's taking the information that you get from the correlation, that relationship that you discover from the correlation, and then using it to make predictions. Using your x variable to then predict your y variable. And why is this useful? Well, it's useful because what if you have a new group of people? Let's say I do a study and there's like 100 people, and I'm able to establish that there's like a strong correlation between two variables. Let's say, from my many years of teaching statistics and other classes at college, and I have been teaching for years. Let's say I've gathered data on everyone for years and years and years. I've asked every single student how long they studied for exams. It was like the first question on every exam. How long did you study? How many hours did you study for this exam? And I'm going to get a bunch of different answers. And let's say I've been doing this for years. So that I'm treating that as my cause, the x variable. How many hours did you study? Now I'm going to use that to create a correlation with then the all of my students' actual test scores. I'm going to calculate a correlation between how much my students study and their test grades. Now, when my new class comes in, I can tell them, hey, by the way, there's a strong positive correlation between the number of hours that you study and your exam grades. And in fact, if you tell me how many hours you plan on studying, I'm going to make a prediction for you on what your exam grade will be. And that's what regression is for. It's for making predictions. It's also useful for description, and we'll talk about that as a part of our discussion today. But its primary purpose is for prediction. Give me some value on the x variable, and I will make a prediction for you on the y variable. That is the use of regression. So, here are some examples of questions that would use a regression approach. And I want you to notice that in each and every one of these examples, there is two variables, two ways that people can be different. And both of them are quantitative. They're dimension-based, meaning high scores versus low scores indicates differences in amount, high versus low. So here I want to predict people's weight from knowing how many calories they eat in a day. So my input is going to be the calories. That's going to be my x. And then I'm going to predict their weights. So that's going to be my output, my y. I want to use the number of hours of TV you watch in a day to predict your regression. So I'm going to use TV watching as my input. That's going to be my x. And then your regression is going to be the output, the y. Notice how they're both quantitative. More versus less TV watching, more versus less aggression. Then I'm going to predict the number of errors in a hospital from the number of hours nurses have to be on call, right? So the idea here is nurses have to be on call. So I'm going to ask a particular hospital, how many hours on average do your nurses are they on call? So every hospital is going to have an input, how many hours the nurses are on call. Then that's going to be the input. That's the x variable. Then I'm going to then predict as the output, the y variable, the number of errors that hospital makes. Or how about this one? The morale at a company, I'm going to use that to predict the company's efficiency, right? So I'm going to take every single employee and I'm going to map their morale. And then based on their morale, I'm going to make a prediction about how efficient that person is. So it's all about prediction. And you're going to know a regression when you see one, when you see that word predict, because that's what it's for. There's vocab terms we're going to need to learn that I want you to put in the back of your head for now. Instead of just calling the variables the x variable and the y variable, we give them special names. We call the output variable, the variable we think is the effect, we call that the criterion because it's what we're interested in making a prediction about. It's the criteria for us, our criterion variable. It is the variable we're hoping to make predictions about. And we call it the y variable, and we track it along the y-axis. The input variable, the variable we think is the cause, we call the predictor because we're going to use it to make predictions. So it is always called the x variable, and it's tracked along the x-axis, the horizontal axis. The criterion is along the y-axis, and the predictor is along the x-axis. And I should let you know that sometimes people get a little sloppy, and they start calling the criterion the dependent variable, and they call the predictor the independent variable. And I'm going to go ahead and call those people wrong. And you can tell them I said so, because that's sloppy. Independent and dependent variables are only for when you have truly true experiments, those things we talked about at the very start of this semester. In the world of regression, where we're just measuring people, along quantitative dimensions, the appropriate terminology is criterion and predictor, not dependent variable and independent variable. But in your future life, you may see an instructor use those terms. They'll call criterion variables dependent, and they'll call predictor variables independent. And that's just inaccurate. It just is. And so in our class, it's important to remember that the output variable, the Y variable, is called the criterion. It's what you're trying to make a decision about, make a prediction about. The X variable is the input variable, the predictor variable, that thing we're going to use to make predictions. And it's all about lines. It's all about creating these lines. And if you remember from our discussion of correlation, I said that correlation is really about seeing how spread out these cloud of dots are around an imaginary line. And regression is about creating that imaginary line. It's called the best fit line. We're trying to determine the one best line that fits through a cloud of correlation dots that then we can use later on to make predictions. It's a line equation. We are going to be using what's called a regression analysis to create a line equation. And if you remember from your previous math classes, hopefully you remember that a line can be defined as an equation. Y equals mx plus b. Hopefully we all remember that equation represents a line. This is the slope, and this is the y-intercept. The slope represents the rise over the run, the steepness of the line, right? The rise over the run. That is how you could determine the slope of a line. And then there's the y-intercept. It is the value of y when x is 0. It's where the line crosses the vertical y-axis. And once you know the slope and the y-intercept, you can plug anything you want in for x and you can spit out a y. And that is then the goal of regression, to create a prediction line called the best fit line. And it's about finding the one line that fits the best through a cloud of correlation dots. And the slope and the intercept have their same mathematical interpretations as they did from math class. Once we get the slope and the y-intercept, we can then use it in bivariate regression to make predictions. Shove in anything you want for the x variable, and you can then spit out a y. That's the idea. So, in the world of behavioral science, however, we like to make your life difficult. And instead of calling it y equals mx plus b, we call it y hat. Now, why is it called y hat? Well, because we're dealing with predicted values, not people's actual scores, but rather what we would predict for them. We're dealing with people's predicted values. So the reason why we use y hat instead of y when we're dealing with regression, to digress, is because y would refer to somebody's actual y scores. But we don't want somebody's actual y scores. Rather, we want to make a prediction in a new group of people of what those y scores would be. So we put a hat on y, and we call it y hat. So it's not y equals mx plus b, it's y hat. We're having a prediction party, so we put a little hat on y. And here is that little hat on y. Here is that little hat on y. So let's use those, and now it's not just x, it's x sub I, right? Because this stands for somebody's individual score on the x variable. Shove in somebody's score on the x variable, and now you can make a prediction for them on the y variable, where we call it y hat. So let's say I want to predict your weight. So I want to predict your weight, not your actual weight, but I don't know your actual weight, right? If I knew your actual weight, I wouldn't need regression, right? I'm going to predict your weight, your y hat, based on knowing how many calories you eat in a day. And so you tell me how many calories you actually eat in a day, your x sub I, and now I'm going to make a prediction for you about what I think your weight is, your y hat, because we're having a prediction party. Or I want to use the number of hours of TV you watch, so you tell me. Tell me how many hours of TV you watch, your X sub I. And then I'm going to make a prediction about how aggressive you are. I don't know exactly how aggressive you are, but I'm going to make a prediction, your Y hat. I'm going to predict the number of hours a hospital makes. So a particular hospital's Y hat, the number of errors they make, based on them telling me how many hours their nurses are on call. So the input is the number of hours nurses are on call. Now I'm going to predict the number of errors the hospital makes. And it's right there in the language. What are you trying to make a prediction about? I'm trying to predict weight. That's the Y. I'm trying to predict aggression. That's the Y. I'm trying to predict the errors in the hospital. That's the Y. Specifically, it's the Y hat. And so then the number of hours nurses are on call is the X. I'm going to use the morale at a company to predict the employee efficiencies. So efficiency is the Y hat, morale is the X. And just to put a finer point on it, regression, just to remind you, talks in terms of cause and effect. X appears to be the input, the cause. Y appears to be the output, the effect. We're using X's to make predictions about Y as if there's a cause and effect relationship. But the math, I promise, is just an extension of the correlation. And so the language can be deceiving. Regression is no more necessarily cause and effect than correlation is. It's just all the language that we use sort of implies a cause and effect relationship, whether there is or not. But it really is just an extension of the correlation. You start out with the correlation, right? Where you're sort of measuring the shape of this oval that surrounds this cloud of dots. That's what the correlation is. You're looking at for how strong, how systematic is the linear relationship between two variables. And what you're looking at is the scatter of the dots, where if the dots are very tightly packed together, not very spread out, if they're really, really close to an imaginary line, then you say that the relationship is systematic. You say that that relationship is strong. You're trying to explain the scatter of the dots. You're measuring the scatter of the dots, trying to see if there's a systematic, strong relationship. And then you standardize it with the correlation so that you can make comparisons and you can interpret that number. But regression is trying to figure out the exact equation, that y equals mx plus b equation that determines and defines the line that best fits through the correlation's cloud of dots. And so each correlation is going to have one regression line that's going to fit the best through the cloud of dots. You're creating the one unique prediction line for that correlational analysis, where you're predicting the y-scores from the x-scores. And then that regression allows us to make a lot of really cool further interpretations. It allows us to say things like this. Well, if someone has an x score of 0, what would be your prediction for y? As y changes, what happens to x? As x changes, what happens to y? Right? For a 1 unit change in x, what might you say would be the change for y? Where would that best fit line be in the graph? Because there's one then y equals mx plus b line equation that best represents that line. So correlation is the spread of the dots. Regression is determining what that imaginary line should be that goes through those cloud of dots. And so even though as we start getting into the nitty-gritty math, it looks like the correlation is step 1, because it is, and then the regression is step 2, and even though it's going to seem like the interpretations of the ingredients of each are somewhat different, they really are two sides of the same coin. The correlation just measures the spread of the dots. How spread out are they? Are they tightly packed around the imaginary line, or are they super spread out around the imaginary line? Is the relationship really strong because they're super close to the imaginary line? Or is the relationship weak because they're spread out along that imaginary line. Regression is just determining what that imaginary line should be. And so just like with a correlation, the regression is a linear analysis. It's trying to find the one line that fits best through the dots. Finding the line, this imaginary line that goes through the correlations cloud of dots, is the whole point of a linear regression analysis, right? The correlation is looking at how spread out the dots are. If there is a lot of scatter around the line, weak relationship. If all the dots are tightly packed around this line, strong relationship. Regression is finding this line specifically, not just eyeballing it the way we've been doing, but actually specifying the one line that fits the best through these cloud of dots. And it is in fact called the best fit line. Another name for it is the lowest fit line. And it's the bottom line is there is one unique line that will fit the best through the cloud of dots, where you want to minimize the errors of prediction. And we'll cover what these errors are in a minute. You want to minimize this term called E. And it's essentially how off the line is for all of the people. Because notice that we can sort of eyeball and create this line here, that each dot here is a person, right? And some of the people fall on the line, like this person right here, right? This person right here fell right on the line. Other people don't fall right on the line. We want to find the one line that minimizes these errors of prediction, because then we're going to use this line to make predictions. So the error then is how off of the line each person is. And you want to find the one line that minimizes these what are called errors, these errors of prediction. And specifically, actually, you're trying to minimize the squared errors. So we're actually, that's just a mathematical reality. You're trying to minimize what's called the squared errors. And we'll return to this in a minute. And another term for error is called a residual, because it's what's left over after you make your prediction. And we'll return to this idea in a little bit. But I just want to get your mind wrapped around this idea that we're trying to find the one line that is the closest to all of the dots simultaneously, right? We don't want to put the line up here so that it's close to these people at the top, because if we did that, then it would be far away from these people at the bottom. We want to find the one line that is the closest to all of the dots collectively. And how off of the line a person is their error. And we're trying to minimize the error. Another term for error is called residuals. And so we're really trying to minimize the squared errors. And the reason for this is because any dot that's above it is going to be off the line, and any dots below it are going to be off the line, but all the dots above it are going to cancel out all the dots below it. And so much like with the standard deviation, we square the errors to find the one line that minimizes the errors around this line. And this is all just concept theory stuff for now. In calculating the line, it's actually a whole lot easier and more straightforward. But I just want you to have that knowledge in your sort of conceptual bag of tricks as you move on to more advanced statistics, if you happen to be a psych major or another major where you're going to have to take more statistics. That technically in regression, when you create the one line, the one equation that will represent the best fit line, you're minimizing the squared residuals. And I'll show you some pictures of that in a little bit. But for now, know that I have a score. There is a prediction line. However, off of the line I am is my error, E, also called the residual. So here is that best fit line through this cloud of dots. And then here would be this person's error. Whew, that's a whole lot of error for this person. Whatever number this is, right? However, off of the line this person is that person's error. This is this person's error. There. Not a whole lot of error for this person. Now, how do we then calculate this regression equation? We'll return to error in a little bit. Well, to make your life difficult, not only do we change the y into a y hat, we change the m into a b and the b into an a. What? I know. I did not make the rules, and I am so not making this up. You are probably familiar with the line equation that looks like this. Y equals m x plus b, where this was where the m was the slope, where b was the y-intercept, and then you could put anything you want in for x, and that would spit out a y on that line. Well, in statistics, we like to make life difficult. Well, in reality, we just do things a little differently than the mathematicians do. We use m in statistics often to refer to the mean, so we can't use it to refer to the slope now, right? And so instead of calling the slope m, we call the slope b. And when we're talking about parameters, we call it beta. Bottom line is, it is b. The new term for the slope is b, not m anymore. Nope, nope, nope. The new term for the slope is b. And our new term for the y-intercept isn't b anymore, it's a. And then we make your life even more complicated by putting the y-intercept first and the slope times the x second. I did not make the rules. These are the conventions in statistical analysis. But don't panic. It really is that equation, y equals mx plus b. We're just changing the symbols. The y-intercept is just now has the symbol a. It still means the same thing that it did before, where a line equation crosses the y-axis. The slope means the same thing as it did before. How steep is the line? The rise over the run. It's just now our symbol for the slope is b instead of m. The mathematicians should change, don't you think? Why should the statisticians have to change? What are you going to do, right? And then x is any score you care to put into. It's someone's actual score for x, whatever you think the input cause predictor variable is. Then you can spit out a predicted value for y, the criterion variable, where x is the prediction and then y is the criteria, sometimes erroneously called the dependent variable. But really it's predictor, criterion, right? And so the whole point of regression is figuring out what this slope is. What will the slope be for my perfect best fit line that will minimize the errors? What will the y-intercept be for my perfect best fit line that minimizes my errors? Once I've calculated the slope and once I've calculated the y-intercept, I now have what's called a prediction equation that I can then use for a brand new group of people. Shove in anything I want for x and spit out a y hat. This is then called the basic model. It's how you get out somebody's actual scores. You remember that error term I talked about? We're not going to use the basic model. You're never going to see this equation again. But I want to share it with you because this exists conceptually and theoretically. To get somebody's actual y scores out, you start with the prediction equation, and then you add in how off the equation was. And that is then the error. And so you want to find the one prediction equation. You want to find the one unique y-intercept and the one unique slope that will make all of these errors, technically the squared errors, as small as you can. You want the predictions that you make for people to be as accurate as you can. And so these are people's actual y scores. This would give you people's predicted y-scores. And then the error is the difference between the y-hat and the y. And you want that error small. You want to minimize the errors of prediction. And so the E is then called the error term. And each person has their own error term. And you want this to be as small as possible. You want the one best fit equation that will make the errors of prediction as teeny tiny as you can get them. And happily, there are mathematical ways we can ensure that this will happen. And so if we compare and contrast these two equations, let's say we have a group of scores, right? We have a group of scores, and we're going to use these group of scores to make ourselves a prediction equation. This equation over here on the right, you put in people's actual scores for X, and what comes out is your prediction for them. You know that because Y is wearing a prediction party hat. Right? Over here, you then add in how wrong the prediction was, how different y-hat was from their actual scores. And then once you have that error term, this equation will actually spit out people's actual scores. Because no matter what prediction equation we make, it's going to be people are probably not going to fall exactly on the line unless we have a perfect correlation where people are falling in a straight line. And so we want to find the best fit equation that minimizes this E, that minimizes this error. And technically, it's minimizing the error terms. And so let's visualize that. Here is error. Once we have created the best fit line here in blue, I then can plug in anything I want for X. So let's say I plug in -1 for X. I come up here, and my prediction on Y for this person is positive 0.25. Do you see how right here would be positive 0.25? Right there. But then I look at this actual person who has a score of -1, and I see that I'm off. Their actual Y score is different than their Y-hat score because only Y-hats will be along this blue line. Let me draw in black. This red is not, I'm not feeling it. So let me highlight this. Let me highlight this person here. This person had a score on the x-axis of -1. This is their actual X score. So here we have a person whose actual X score is -1. And so I plug in -1 to my prediction equation. And then I find out that my prediction for them is wherever -1 intersects with the prediction line. So, right here. Here is my prediction for this person down here, right? This distance between their actual score, which was here at, if I eyeball that, it looks like -1.75. So their actual Y score was -1.75. But my prediction for them was actually up here, right? I can eyeball that, and it looks like -0.75. Yeah, -0.75, because that's where this is along the y-axis. And so their y-hat is -0.75. So there is a residual. There is an error. The error of prediction is by about 1. So the error term for this person is 1. That's how off of the line my prediction was. But the error term for this person who had a score of -1 was 1, right? That's how off of the line it was for them. This person over here is going to have a much bigger error term because my prediction for them was around 0, and where they actually were was 2.5. So their error term was 2.5. This person, I predicted for them to be at positive 0.5. Where are they really? They're up here at 2. So their error term was 1.5. right? So these are errors of prediction, right? And so what you want then is to minimize the error, right? You want to minimize these residuals. You want to find the one line that minimizes these errors of prediction, because you wouldn't want to just redraw the line. Because let's look at this person here. This person had an X score of 51, and here's where their actual Y score was, somewhere around 78. What I predicted for them, though, was all the way down here at 69, right? 69 compared to 78. Wow, that's like a 9-point difference, a 9-point residual. But I wouldn't want to just redraw the line. I'm going to draw the line up here to make this residual small. No, because that would make this residual ginormous. The idea behind regression is to find the one line that looks at all of the errors, and makes them as small as it can be. And technically, you're minimizing the squared distances. What the residuals are, what the error terms are, is how off of the line all of your people are. You're going to create this best fit line. You're going to find the one slope and the one y-intercept to create one line equation that we call the regression or prediction line. And then this one line is going to minimize the squared residuals, the squared errors, how off of the line the people are. And so just tuck that in as concepts. We're not going to be actually calculating any residuals. We're not going to be calculating any squared residuals. You just need to know that once we have our prediction equation, it does in fact minimize the squared distances between people's actual scores and the prediction line. So this person had a score of 51 up here. I was going to predict he had a score of 69, but in reality, he had a 78. That is a residual. It is an error term. This is this person's error term. And I want to find the one line that minimizes everybody's error term. And if I do the math right, I will in fact create that best fit line. So, to summarize, we are going to create an equation that looks like this. We're going to be able to put anything we want in for X, people's actual scores on the predictor variable, the cause, the input, the predictor. We're not going to spit out people's actual scores. We're not spitting out people's Y scores. What we're actually going to get are people's predicted scores. And then once we have the one slope and the one y-intercept, we can put anything we want in for X, and we can then spit out a y-hat, a predicted value. And if we do it correctly, if we find the right slope and the correct y-intercept, the correct B, which is our new symbol for slope, and the correct A, which is our new symbol for y-intercept, once we have these two values, we will in fact have found the one line that makes the y-hats as close to the y's as we can get them. Finds the one line where the y's are as close to the y-hats as we can get them, where the errors of prediction are small. And so this then is the equation for the best fit line. And how are we going to get this line? The only two things we're going to need to calculate are this. We're going to need to calculate the slope, and we're going to need to calculate the y-intercept. That's it. And then once we do that, boom, we have the best fit line that will fit through any cloud of dots. Hooray! And so we're going to need to calculate the slope, and we're going to need to calculate the y-intercept based on the information that we got from the correlation. Because remember, regression is just an extension of the correlation. That's all it is. Because the regression line, the best fit line, is going to be based on the unique constellation of cloud of dots that the correlation creates. And so here is how you calculate the slope. You can either calculate it like this, or you can calculate it like this. These are what are called algebraically equivalent. To calculate the slope, you can take the covariance between x and y and divide it by the variance of the predictor. Notice how it's s squared. This tells me it's the variance, not the standard deviation, but the variance. And not just of any old variable, but the variable that I have chosen as the predictor. Because remember, regression makes you pick. What is your input? What is your output? What is your predictor? What is your criterion? What is your cause? What is your effect? And so to calculate the slope, you take the covariance of x and y, and you divide by the variance of the predictor. And that will give you the slope, the steepness of the line, the rise over the run for your line. Another way of calculating the slope is like this. You can take the correlation of x and y, which is just the standardized covariance, remember, and you can multiply it, right? This is multiplication. You can take this number and you can multiply it by the quotient, which is just division, of the standard deviation of your criterion divided by the standard deviation of your predictor. Notice how there are no squares here because these are standard deviations. And notice how the criterion, the output, the y variable standard deviation goes on top. It's not arbitrary. And the standard deviation of x goes on the bottom. No matter which one you use, the x variable is going on the bottom. Here, the variance of x goes on the bottom of the fraction with covariance on the top. Here, the standard deviation of x goes on the bottom of the fraction with y, with the standard deviation of y over the standard deviation of x, and then you take this quotient and you multiply it by the correlation. They're algebraically equivalent. I like this one better because it only deals with two numbers. And if I've already calculated the correlation, it's two numbers that I've already calculated. And we'll do an example of that as a part of today's lecture. Here is how you calculate the y-intercept. You take the average for your criterion, because again, regression makes you pick. You can't put any old average in here. It has to be the average for your output, your criterion variable, your y variable. You take that and you subtract the slope times the average of the x variable. These are averages. This is not y hat. Don't get confused. Y hat is your predicted value. This is the average of y, y bar. This is the average of x, x bar, right? So notice you're going to have to calculate the slope first, but once you do that, take the slope, multiply it by the average of x, then take your average of y, and then you subtract. And if you've already calculated the covariance and the correlation, and once you calculate the slope, you already have all these numbers, and it's just plug in and solve. And so notice the flow. First, we calculate the covariance. We use the covariance to calculate the correlation. Once we know the correlation, because we've had to calculate the two standard deviations, we can then get the regression. We use all of those things we've already calculated to get the slope, and then we use that to get the y-intercept. Where the slope is where the regression is interested in the slope of the line, so we can make predictions, isn't trying to estimate the amount of scatter. Where the correlation is trying to figure out how scattered out the lines are. But correlation and regression are mathematically and conceptually linked, right? The slope of the line depends on the scatter. The slope of the line depends on the correlation, the covariance, right? It's right there in the equation, right? The slope is going to depend on the covariance or the correlation. So the scatter of the dots, the cloud of the dots, determines what the slope is going to be. They're related. They're just focused on different aspects of the same analysis. So, to review, we're trying to find the best fit line through a group of dots, right? Through that scatter plot. We're gonna do that. We find the best fit line using those equations I just taught you, and the regression is called a least squares analysis because we're trying to minimize the squared errors. We're trying to minimize how off of the line our people are. We're going to create this one regression equation, and once we've done that, we're going to have the one best fit line that minimizes how off of the line, because the line is all the Y hats. All of our actual Y scores are people's actual data. And regression is useful for prediction, of course. It's useful for predicting Y hats, right? I'm going to write Y hat there, right? It's useful for predicting Y hat scores, and it is useful for description. You can actually interpret the slope and interpret the Y-intercept. And so how can we interpret the Y-intercept and the slope? Well, the intercept is the value of y when x is 0. But now we're actually dealing with variables. And so whatever your x variable and your y variable is, if someone tells you they have a 0 on the x variable, the y-intercept, the a, is what you would predict for them. The slope is also interpretable in terms of actual human variables, right? Because it tells you how steep the line is. It's the rise over the run, but you can actually interpret it. Because let's say the slope is 1.2. That is the slope. Well, if you have two people in your sample, one with an x score of 5 and the other with an x score of 6, you would expect the difference between them to be about 1.2. The slope is for a 1 unit change in x. The y is going to change about a slope. And so let's say the x variable in this example is the number of hours that you exercise, and that's your x variable. And let's say the y variable is an index of health. Well, so for every 1 more hour you exercise, I would expect your health index to go up 1.2 health units. That is how you can interpret the slope. It is for every 1 unit change in x, there will be a slope unit change in y. It is the change in y for a 1 unit change in x. And we'll go over an example of this right now. So here we have two variables, coffee and sleep. And I suspect that coffee is affecting how much people sleep. I want to use how much caffeine, how much coffee people drink to predict how much sleep they get. So coffee is going to be my x variable and sleep is going to be my y variable. And I'm going to use people's actual x scores and their actual y scores to create a prediction equation that I can then use with a new group of people. I'm going to use my x scores and my y scores. I'm going to use the correlation between them to create my prediction equation, my regression equation that I can then use with a new group of people. So here is my data. Here's person 1 and how much coffee they have, 3 cups a day. This is how much that person sleeps, 7 hours a night. Person 2, they drink 2 cups of coffee. They drink 10 hours a night. They sleep 10 hours a night. Person 3, they drink 4 cups of coffee and they get 5 hours of sleep a night. Person 4, they drink 5 cups of coffee and they sleep 5 hours of sleep a night. Ugh, I can't speak today. All right, let's start again. Person 1, 3 cups of coffee, 7 hours of sleep. Person 2, 2 cups of coffee, 10 hours of sleep. Person 3, 4 cups of coffee, 5 hours of sleep. Person 4, 5 cups of coffee, 5 hours of sleep. Person 5, 1 cup of coffee, 8 hours of sleep. So now, in order to calculate a regression equation, I'm going to have to calculate the covariance and the correlation first. So the first thing I'm going to need to do is calculate the average for these two variables. So I take 3 plus 2 plus 4 plus 5 plus 1, divide by 5. To get the average for coffee intake is 3 cups of coffee a day. So my x bar, the average for coffee is 3. 15 divided by 5, because 3 plus 2 plus 4 plus 5 plus 1 is 15. Then I do the same thing for sleep, because coffee intake is x and sleep is y. I'm going to use coffee intake to predict sleep. So I do 7 plus 10 plus 5 plus 5 plus 8. That gives me 35. 35 divided by 5 is 7. So the average sleep that these 5 people get a night is 7. So I have 5 people. Big Mama N is 5. where I've tracked two quantitative things about these individuals. Two quantitative variables, coffee intake, more versus less, sleep, more versus less, and now I have the two averages. I have the average for coffee intake of 3, and I have the average of sleep of 7. And so now I'm going to get the covariance between them. And here is that equation from last time for the covariance. I subtract the average of all the x scores from all the x's, right? So 3 minus 3, why? Because 3 is the average of x. 3 minus 3 is 0. 2 minus 3 is negative 1. 4 minus 3 is positive 1. 5 minus 3 is positive 2. 1 minus 3 is negative 2. I have all of these deviation scores for x now. Then I do the same thing for the y variable. The average for y is 7, so I take the data set for y. 7 minus 7 is 0. 10 minus 7 is 3. 5 minus 7 is negative 2. 5 minus 7 is negative 2. 7 minus 7 is 0. Here are the deviation scores for x. Here are the deviation scores for y. This is person 1, person 2, person 3. I'm tracking coffee and sleep among the same people. I could create a scatter plot of 5 dots, but that would not be very useful, right? This is made up data. I would never have a data set of 5 people in real life, but it allows us to calculate it. So my next step, I've done this, x minus x bar. I did all that. I did y minus y bar. I did all that. Now what do I need to do? That's right, get the cross product of the deviation scores. Multiply the deviation scores for x by the deviation scores for y. And so I take 0 times 0 to get 0. I take negative 1 times positive 3 to get negative 3. I take positive 1 times negative 2 to get negative 2. I get positive 2 times negative 2 to get negative 4. Negative 2 times 0 is 0. So notice, this person was below average on coffee intake, above average on sleep. This person was above average on coffee intake, below average on sleep, giving me a negative cross product. This person was above average on coffee, below average on sleep, giving me a negative cross product. So when I add them together to get the sum, I'm going to end up with a negative number, a negative relationship. The more coffee you drink, the less sleep you're getting. So my next step, now that I have all these cross products, because you're multiplying across, getting the products across the columns, now I'm going to add them up. I take 0 plus negative 3 plus negative 2 plus negative 4 plus 0 to get negative 9. I'm now adding them up, starting at the first person, going to the last person, and adding up all of their cross products. Then I divide by n minus 1 because this is a sample. And just like variances can be underestimated, so can covariances. Take negative 9 and divide by 4. Why? Because n is 5. There are 5 people. So I take negative 9 and I divide by 4 to get negative 2.5. Why am I doing that? Because that's what the equation tells me to do. First I add them up. Then I divide by n minus 1 to get negative 2.25. The covariance of x and y is negative 0.25. Well, now I need to get the correlation. And in order to get the correlation, I need the two standard deviations. Because remember how we get the correlation. This is how we get the correlation, remember? You take the covariance of x and y, which we've just calculated, but you need to then divide by the product of the two standard deviations, which means we're now going to need to get the two standard deviations. Well, now we need to get them. Happily, I've already calculated the deviation scores. When I calculated the covariance, I already calculated the deviation scores. So I'm just going to borrow those deviation scores that I've already calculated and then square them as my next part of getting the standard deviation, right? I've already calculated those. So I've just borrowed those deviation scores of 0, negative 1, positive 2, and negative 2 for the x. 0, positive 3, negative 2, 0 for the y. And so now I square those because that's what the equation for the standard deviation is. Here's the equation for the variance, right? Take the square root of it to get the standard deviation. So have I already gotten the deviation scores for X? I certainly have. Have I already gotten the deviation scores for Y? I certainly have. The only thing that would be different is this would be an X and this would be a Y bar. This would be a Y and this would be a Y bar, but it's the same form. Remember that from last time? Hopefully you do. I'm just calculating the two standard deviations, the standard deviation for X and the standard deviation for Y. And here's that equation for the variance. Take the square root of it to get the standard deviation. So square the deviation scores. 0, 1, 1, 4, and 4. 0 squared is 0, negative 1 squared is 1, positive 1 squared is 1, positive 2 squared is 4, negative 2 squared is 4. Do the same thing over here. The deviation score is 0, square it to get 0. Deviation score is positive 3, square it to get 9. The deviation score is negative 2, square it to get 4. Deviation score is negative 2, square it to get 4. The deviation score is 0, square it to get 0. So now I've got the square deviation score for X and the square deviation scores for Y. What's the next step? I add all those up to get the sum of squares. So I add 1 plus 1 plus 4 plus 4 is 10. That is the sum of squares. For X, I add them up over here. 0 plus 9 plus 4 plus 4 plus 0. That is the sum of squares for Y. Divide by 4, because these are samples, to get the variance of X is 2.5. This is the variance of X. Do the same thing for Y. 17 divided by 4, because that's n minus 1. 4 is n minus 1. To get the variance of Y, which is 4.25. I simply take the square roots of those to get the two standard deviations. So, to summarize the things we've calculated so far, if you're keeping track, we've calculated the average of X, which was 3. We calculated the average of Y, which was 7. We were able then to use those averages to calculate the covariance of X, of XY. The covariance of XY, which was negative 2.25. That was the covariance of X and Y. We then used the covariant. After that, we used the averages of X and Y to calculate the variance of X, which was 2.5. Then we calculated the variance of Y, which was 4.25. We took the square root of 2.5 to get 1.58. We took the square root of 4.25 to get 2.06. Now we have the covariance of X and Y, negative 2.25. To get the correlation, we take the covariance and we divide by the product of the two standard deviations. We take 1.58 and we multiply it by 2.06 to get 3.25. We take negative 2.25 and we divide it by 3.25 to get the correlation of negative 0.69. That is the correlation that we can now interpret. It's fairly close to 1. It is a large equation. It is a strong negative correlation using those rules of thumb. It's above 0.5, so it's a strong relationship, and it's a negative correlation. That means as coffee intake goes up, sleep goes down. People who are drinking more than average for coffee are getting less sleep, and people who are drinking less than average for coffee are getting more sleep. There's a negative relationship between these two variables. But now I have to get the slope and the y-intercept if I want to use how much coffee people drink to predict how much sleep they get. So I do just that. And here is my equation for the slope using the covariance of X, which was negative 2.25. See, I kept track of it. And the variance of X, which is right up here, 2.5. That will give me my slope of negative 0.9. Negative 2.25 divided by 2.5 is negative 0.9. That is the slope. For a 1 unit increase in coffee intake, it's a negative slope, right? It's a negative 0.9. For every 1 more coffee beverage someone drinks, I would predict they get 0.9 less hours of sleep a night. There would be a 0.9 decrease in sleep in hours. For one more coffee drink they have, there will be a 0.9 hours decrease in sleep. Now, I can also calculate the slope this way. I can take the negative correlation of negative 0.69 and I can multiply it by the standard deviation of y over the standard deviation of x. So 2.06 over 1.58 is 1.3. I take 0.69, multiply it by 1.3, and what do you know? I also get negative 0.9. They're algebraically equivalent, these two equations here. I like this one because it only involves two numbers, but I'm going to have to remember that it's the variance of x that goes down here, the variance of x. And that is the predictor variable, and it is the variance, that one step before the standard deviation when you're calculating. I also need to get the y-intercept. So I take the average of y, which was 7, and I'm going to subtract the product of the slope, which I just calculated, negative 0.9, times the average of x, which was 3. So I take 3, and I multiply it by negative 0.9 to get negative 2.7, because you can totally have a negative slope. Just means that the slope is in the negative direction of the line. And so I then, to get the y-intercept, I take 7 and I subtract negative 0.27. Well, when you subtract a negative, that just gives you a positive, right? Remember back from your previous math classes. So I take 7 and I subtract negative 2.7. That gives me a positive 9.7 because subtracting a negative is really like adding, right? And so now I have a y-intercept of 9.7. And I can interpret this as well. If somebody tells me they drink 0 cups of coffee, I'd predict they get 9.7 hours of sleep a night. That is my prediction for them because that's what the y-intercept is. It's the value of y when x is 0. If you tell me you drink no cups of coffee, your x is 0, I predict you sleep 9.7 hours a night. I can interpret not only the slope, I can then use it for description. I can also interpret the y-intercept. I can use it for description, right? Because the slope is negative 0.9, I would predict that someone who drinks 1 cup of coffee versus 2 cups of coffee, the person who drinks 2 is going to get 0.9 hours less sleep a night compared to the person who only drinks 1 cup of coffee. So now let's use our prediction equation. Let's use it. Here it is. Here is my prediction equation. Here is the slope, negative 0.9. Here is the y-intercept, 9.7. Boom, I have a line equation. I have a line equation, y equals mx plus b, except now m is called b and the y-intercept is called a. Don't make the rules, sorry. But here it is, here's that line equation. I can now put anything I want in for x, multiply it by the slope, add in the y-intercept, right? And now I will get a predicted y. So I had 5 people in my original data set, right? Here are those 5 people in my original data set. I used these 5 people to first get the covariance of negative 2.25. Then I got the 2 standard deviations for these 5 people, standard deviation of x, standard deviation of y. Then I used that to get the correlation for these 5 people for the relationship between sleep and caffeine. As the more caffeine you drink, the less sleep you get. Then I was able to use this information to calculate a slope of negative 0.9 and a y-intercept of 9.7. Now I have a prediction equation. This is my prediction equation. This is the equation that represents my best fit line. This is it, right here, right here. Now I can use this with new people. So let's say another person comes along, x sub 6. That means a 6th person, right? As another person comes along and I say, hey, 6th person, not from my original data set. 6th person, come on over here and tell me how much coffee you drink. Come on, tell me how much coffee you drink. And they go 1 cup a day. So I say, okay. So I put 1 in for x. I multiply 1 by negative 0.9 to get negative 0.9. I take 9.7 and I subtract negative 0.9 because I'm adding this negative number and that's just subtraction, right? Right? Negative 0.9 times 1 is negative 0.9, right? So 9.7 minus 0.9. So I now predict for them that they get 8.8 hours of sleep a night. This was a brand new person. They told me they drink 1 cup of coffee, so then used my prediction equation to make a prediction for them. Now let's say another person comes along, a 7th person, X sub 7. This is a brand new person, and they tell me they drink 4 cups of coffee. So now I plug in 4 for their X. I take 4 and I multiply it by my negative slope, negative 0.9, to get 3.6, negative 3.6. I take 9.7, I add that negative number, which is just like subtraction, to get 6.1. So for this 7th person, I would predict that they get 6.1 hours of sleep a night because they drink 4 cups of coffee. And thus is the power of prediction, the power of the prediction equation. I can use it to make decisions about brand new people, which is awesome. Now, more theoretical considerations. There are some assumptions of regression, much like there was assumptions of the independent samples t-test. There are some assumptions for both regression and correlation. And here they are. You assume what's called multivariate normality of the residuals. Ooh. And the reason I taught you about errors, even though we're not even going to calculate them ever, is because I want you to know what they are. Remember, the errors of prediction are about how off of the line people's actual scores are compared to what we would predict for them, right? Well, we assume that the residuals are normally distributed, that most people are packed close to the line, and as you get farther and farther away from the line, there are fewer people out there. It's called multivariate normality of the errors or the residuals. You also assume independence of observations, that none of your people influence each other at all. You also assume homoscedasticity, which is just a fun word. And what it means is you assume that no matter where you look along the regression line, you see equal spread. And I'll show you what that looks like in a minute. Equal scatter around the line. And then last, you assume linearity. You assume that a straight line fits the data pretty well. And so you can't use regression for nonlinear effects. Remember, just like you couldn't do a correlation for nonlinear effects, you can't do a regression with nonlinear effects as well. So no looking at the regression of stress and success, right? Because that had that nonlinear relationship. Here is an example of a violation of homoscedasticity. Here you can see that this regression line is doing real well for these people down here. The errors are low here, but the errors of prediction are really high up here. This is an example of a violation of homoscedasticity, not equal spread around the line, right? I just want to give you a sense of that. And the last thing I want to cover for regression is when not to do it. Because the power of regression is being able to use our prediction equation to make decisions about new groups of people. It's one of the purposes of regression. One is to just describe. You can describe the slope. You can describe the y-intercept. It's a powerful description tool as well. You can interpret the y-slope and interpret the y-intercept just like I did here, right? I interpreted this slope and I interpreted this y-intercept. But the real power of regression comes in our ability to predict, like we did here with 2 brand new people. But you have to be careful when you are making predictions about new people. You have to be careful not to extrapolate. And it's essentially like this. You cannot use your prediction equation for scores that are outside of the original range of X. And so let's go back to my original data here. Notice how my original range of X was from 1 to 5. The highest person drank 5 cups of coffee, and the lowest person drank 1 cup of coffee. And so it was based on scores of 1 to 5 that I created my prediction equation. It's really important that any new people come along have to also be between 1 and 5. Otherwise, you're doing something called extrapolating. Because let's say you create a prediction equation using people's actual SAT quant scores and their actual SAT verbal scores. Now, let's say you're going to predict their quant scores from their verbal scores. And you decide, just for laughs, to shove an 0 into your equation. Let's see what somebody's quant score would be if they got a 0 on the verbal score. Well, nobody gets 0 on the verbal score. You can't get 0. And so you're going to have a meaningless prediction. It can be just completely meaningless, right? So you don't want to extrapolate because, one, your predictions might be meaningless. Like in this example, because SAT scores cannot equal 0, what would your prediction even mean? It would mean nothing. But another reason not to extrapolate, to not go beyond the original range of your X variable, is because sometimes prediction equations look different at different ranges. Let me give you an example of this. Let's say in a group of college students, you create a prediction equation. And so let's say your X variable only ranges from 18 to 25, right? You create a prediction equation based on X scores of 18 to 25-year-olds. Because maybe there's a strong positive relationship between age and happiness among 18 to 25-year-olds. And so, but let's say someone comes along, a new person who has an age of 60, but you used an equation that was based on X scores of 18 to 25. It very well may be that the relationship between age and happiness is very different at other ranges of X. This may be one of those parabola-shaped, quadratic, nonlinear effects, but you don't know that because your prediction equation was only based on 18 to 25-year-olds, right? The slope and intercept may be very different among older folks, so don't extrapolate. Whatever your original range of X was, those are the only kind of X's you can then plug into your prediction equation with a new group of people. Don't extrapolate. And here is a very funny example of extrapolation, once again from my friend Randall Monroe at XKCD. And he xkcd.org. He's .com. He's great. And so here is what he's done. He has used 2 data points to create a prediction equation. Here he's got days of the week along the x-axis and the number of husbands along the y-axis. And you can create a prediction equation, a line equation, with just two data points. That's all you need. And so here, he had day number 0, and on day, that was his X score. And then he had husband, you had 0. That was the Y score. And then there was the first day. That was the X score. And you had 1 husband. So that was the Y score. Oops. And what he's done then is create a perfect prediction equation where what's going to happen on day 2? Well, what's going to happen on day 2 is you're supposed to have 2 husbands. What's going to happen on day 3? You're going to have 3 husbands. What's going to happen on day 4? You're going to have 4 husbands. But if you look at the original range of X, was only 0 and 1. So you cannot use other ranges of X. You can't plug in 2 and 3 and 4 and 5 because that is extrapolating. Don't do it. All right? All right, that's regression, just a mathematical and a conceptual extension of correlation. See you next time where we talk about chi-square.